From a visual inspection, crime scenes investigators were unable to trace any blood staining. Hence, a highly sensitive luminol test was delivered. In addition to this, portion of the red stained clothing was removed from the victim and analyzed with Casimir test in order to determine the presence of blood. Latent fingerprints analysis was carried out on the cell phone, headlight and the red packet for further confirmation that the victim was the only one who worked on the day he died. Mixture of the unknown loose granular black and blue material were then tested with atomic emission spectroscopy to identify the substance. The unknown liquid, undigested substances from the victim, and the unknown tablets in the red packets as well as the blood samples were all examined with gas chromatography and gas chromatography mass spectrometry for further clarification. Furthermore, it was found that both right and left tibias of the victim were critically fractured and 2 tiny puncture marks were noted on the right swollen calf muscles. White discoloration were also visible on the victim's fingernails. The blood samples which brought back to the lab from the crime scenes were also found coagulated. Some common symptoms of arsenic poisoning. Arsenic poisoning is a critical condition caused by ingestions, absorptions, or inhalation of a significant level of arsenic, and it can be found all over the globe in groundwater. Arsenic typically have no flavor or odor, hence it is extremely hard to be detected. And inorganic arsenic such as arsenite and arsenate is very toxic to most biological systems, including human beings. And in the absence of treatment, 70 to 180 mg of arsenic is enough to kill an adult. The another possible cause of death was the venom from the rhesus viper. It undergoes a cascade reaction which either encourages or disseminated intravascular coagulation that can affect various human vein vascular organs such as the kidney and heart, and this may eventually result in death. After all the evidence were considered and examined, forensic reports stated that it is most likely that the victim has died of rhesus viper venom and arsenic poisoning. However, various tests must be performed in order to rectify this theory, and these including Casimir test, luminol test, DNA test, latent fingerprint test, AES test analysis, GC test, and GCMS test. Casimir test uses both chemical indicators, phenolphthalein and hydrogen peroxide, to detect the possible presence of hemoglobin in blood. In this case, a presumed blood samples of the red stained clothing from the victim was collected with a swab. A drop of phenolphthalein was then added to the sample, followed by a drop of hydrogen peroxide. The swab turned into pink rapidly, and this indicates that the result is positive. Hemoglobin acts as a peroxidase in the presence of hydrogen peroxide, reducing the peroxide to water, hence causing depletion of electrons in hemoglobin and resupplied by phenolphthalein, which in turn alternating the phenolphthalein back into the intense color phenolphthalein. Since murderers are able to clean up the blood, however, some evidence will still remain. A highly sensitive forensic chemical called luminol was used to detect any hidden blood stains at the crime scene for further confirmation that the victim was or was not murdered. Luminol reacts in a similar way to Casimir. Instead of the color change, it produces energy as light. Luminol powder must first be activated with hydrogen peroxide and hydroxide ions in water, which will then produce energy in the form of light. But in order to accelerate the reaction to produce strong glow, a catalyst is needed. In this case, the iron in hemoglobin is served as a catalyst, and this reaction is known as chemiluminescence. Luminol reacts with hydrogen peroxide and hydroxide ions, and with the presence of ions in hemoglobin will only speed up the reaction, yielding nitrogen and 3 moles of amino phthalate at its excited states. Hence, the product is very unstable, which in turn causing blood stains can be made to glow with a blue light. Glowing blood stains were found 100 meters further away from the crime scene after luminol was scattered. This means that victim was bleeding 100 meters away from where he died. Hence, the possibility that victim was murdered has been raised. However, DNA of blood samples from the victim, luminol test and Casimir test were tested in order to confirm the theory. The DNA fragments were separated by size as they moved through a gel matrix with the presence of electricity, and this process is known as gel electrophoresis. However, DNA must first be glitched into smaller segments with restrictions enzymes in order to compare the DNA samples from the crime scene. To create an electrical field within the gel was submerged into a buffer, and an anode positively charged due to oxidation is placed in the opposite direction of an DNA samples where the cathode, negatively charged due to reduction, is located. This is because the phosphate backbone of the DNA has a negative charge, hence the samples will migrate from the negative to the positive end of the gel. Smallest fragment of DNA will migrate the furthest as it is easier to be pushed through the gel spores by electrical field. Samples will then mix with dye to increase visibility of the results. It can observe that blood samples from the luminol test and the Casimir test will both match with the blood samples from the victim. According to the DNA results, no murder suspects were found. Hence, this proved that the blood stains from the clothing and the crime scenes were both belongs to the victim. Fingerprints identification methods such as fine black powder with brush have been used to examine the headlight, cell phone and the red packet from the crime scene in order to identify any suspected criminals. Latent fingerprints examination results were then interpreted and evaluated. It can observe that both fingerprint samples will match, hence contributing to the fact that the victim was the only one who works on the day he died. Therefore, latent fingerprints analysis will only enhance the fact that the victim was not murdered. Atomic emission spectroscopy can be used to identify an unknown element, as each element produces a unique emission spectrum. In this case, it is required to test the unknown mixture of loose granular black and blue-green materials from the crime scene, which thought to be one of the causes of death. The sample is placed between the carbon arcs to be heated by electric current. The emitted radiation is then passes through the prism with the presence of a silt, spreading the light into numerous wavelengths. This unique beam is then collected on a photographic plate. The emission spectrum of the unknown element is then generated. And here are some of the known spectrum of possible elements. When the unknown mixture is heated, electrons absorb energy and jump to the next higher energy level. And upon cooling, the electrons would fall back to its ground state. Hence, this movement of electrons give up energy as light. By comparing the unknown emission spectrum with the known spectrum, it can clearly be identified that the unknown compound has a mixture of carbon and copper-2 chloride. Copper-2 chloride is one of the halide compounds, which is a binary compound with the halogen atom chlorine and copper-2 that is less electronegative than the halogen, so that the halide contains polar bonds. Furthermore, the slightly positive charged copper in the copper chloride bonds is the source of the reactivity which is shown by the halides. Copper-2 chloride is a light brown solid that absorbs moisture to form a blue-green dihydrate, and it occurs naturally near fumaroles. In this case, copper-2 chloride may absorb moisture from the fumarole steams or from the victim's body. The most common potential health effect of copper-2 chloride is skin burning. Therefore, this supports the theory that the unknown mixture of loose granular black and blue-green material is very unlikely to be a cause of death, since copper-2 chloride will only cause a mild skin burns. Gas, liquid or gas chromatography is probably one of the most commonly used in forensic crime scenes for separating and analyzing compounds that can be vaporized without decomposition. In GC, the mobile phase is known as a gas such as helium or nitrogen due to the fact that they have a low density and a very low chemical reactivity. They carry the component of the mixture over the stationary phase. In this case, the stationary phase is the column coated with a high boiling point of liquid, and the component of a mixture leave the column in the order of volatility, the most volatile first. Before beginning a separation, the operator must first calibrate the flow rate of the gas, mobile phase, and the temperature of the oven in order to fully vaporize the sample, and the flame ionization detector must be lit. In this case, blood samples from the victim was injected into the injection port. The sample is then passed through the column which kept in a temperature-controlled oven. Furthermore, the properties of the column is chosen for a specific separation that is to be carried out. The components of the mixture are then carried through the column by helium gas, mobile phase, from the supplied gas cylinder. In addition to this, the more volatile the component, the less it will interact with the stationary phase, which in turn reducing the retention time. The detector will then detect each component of the mixture after it passes out from the column, and also measures its amount. The detector has a flame ionization detector that contains of hydrogen flame combusting in air. As the substance leaves the column, it burns in this flame, producing ions that can be detected by measuring the electrical conductivity of the flame. However, gas chromatography itself requires a unique mass spectroscopy for further confirmation of the peak's identity. The only difference between GC and GCMS is that GCMS has an addition mass spectrometer attached to its gas chromatography. The MS is then used to identify chemicals according to their molecular structure. The products from the GC are migrated to the mass spectrometer through the transfer line, and the positive ions are formed by bombardment of the samples by the beams of electrons. The ions are then accelerated by an electrical field and then deflected in the curve by further electrical field, which in turn bending through the magnetic field and then further deflected by another electrical field at the end of the detector. Figure 13 shows the mass spectrum which produced from the chemical found in the victim's blood. Compare these to figure 14, 15 and 16 in order to identify what substances, if any, were found in the blood. It can be observed that all three substances including theophylline, a high level of iron and arsenate were all found in the victim's blood as seen in figure 13. As the mass spectra of all the unknown components in the blood match 100% with the known mass spectra of theophylline, iron and arsenic. Furthermore, it appears to be a significant level of these substances in the blood samples. Hence, the toxicology information highlighted the fact that arsenic poisoning was one of the causes of death. However, in order to confirm this theory, the unknown liquid from the puddle and the unknown tablets as well as the undigested substances from the victim's mouth were further investigated with GCMS, and the results are shown in figures 17, 18 and 19 respectively. By comparing these unknown substances, figure 17, 18 and 19 with the known substances from figure 14, 15 and 16, it was found that the unknown liquid from the puddle is arsenate. The unknown tablets from the red packet contains theophylline and iron. It was also found that the undigested substances contain a high level of arsenate, a high level of theophylline and iron. In this case, it can be noted from the result that iron appear on the mass spectrum first and followed by arsenate and theophylline. Their individual standard atomic weight per mole are presented here. In a broad sense, the more polar molecules tend to stick to other polar molecules, and similarly for non-polar molecules. However, the column is made up of non-polar polymer chains. Hence, iron element itself is very polar, which doesn't tend to interact with the column wall. On the other hand, arsenate molecule is considered as moderately polar and theophylline as non-polar. Hence, lots of theophylline molecules will tend to interact with the column wall. Therefore, this explains the order of the mass spectrum results. Therefore, this can be concluded that arsenic poisoning was definitely one of the causes of death, since arsenate was found in the victim's mouth. This also explains that the victim took theophylline and iron tablets to remedy his anemia of iron deficiency and asthma.